Good morning. Welcome to this morning's cleaning debate. I have a very distinguished panel joining me today. From our extreme right, we have Lothar Henneken from Robert Bosch. Then to his left, we have Steve Stach from Austin American. To his left, we have Mike Bixenman from KYZEN Corporation. And to my extreme right here, we have Graham Naisbitt from Gen 3. Thank you for joining us, gentlemen. Now, rose testing is the most common form of cleanliness testing, but many cleaning experts prefer to use SIR to verify board cleanliness. Let's discuss some of these points. The first question I've got is that I'm hearing that J standard 001 is being revised and that the 1.5 milligram per square centimeter its equivalence is being removed. Is this true, and can you explain why? And I think you are probably pretty close to the standards, so let's start with you, Graham.
Okay. Well, the situation is that for the last 2 years we have been working very hard on the Rev G of J Standard 001, and an issue that has always been in the industry is whether or not this number of 1.56 is a good metric by which to control your assembly and manufacturing process. What has come from this is finally the realization and acceptance that it can never be and never was a cleanliness test. It is a process control tool. So in Rev G there will be issued by unanimous agreement of the committee on Saturday to issue an amendment along with a white paper that explains the changes that are now being implemented that force companies to prove the manner and method by which they are developing their process. That's not to say that everybody has to redo it, but if you've got good evidence to support the fact that that is a technique that has worked for you, if it ain't broke, don't fix it. But to move forward, the correct way to deal with these particular subjects is to use changes to insulation resistance. In other words, SIR, which is increasingly now being used by companies. Indeed, Robert Bosch and Lothar Henneken presented a paper on Monday afternoon that demonstrates the validity of all that's been said.
Well, that's quite a statement. Let's move on from that a little bit and ask you, Mike, I mean, what is your view on first of all, the 1.56 milligram level? Do you think that's appropriate? Should it be changed? What's your feeling?
Why don't we frame it in a little different way than what Graham did, and Graham did a nice job. If you think about the rose testing methodology, that was developed close to 30 years back in looking at, the military people in building to a standard, wanted to look at a process control method at the manufacturing site that could help them determine if that board met their cleanliness standards. But if you think about the boards that were being built 20, 30 years ago and compare them to the assemblies that are being built today, there's a lot of difference. Yeah. And within that difference is you're looking to control your process and say, is my board meeting a certain cleanliness spec? There's no one measurement that can do every one of those measurements. You need some level of variability. The rose method, just as what Graham said, can be a process control tool, and it can be used as a part of the manufacturing process. But there are other ways that companies need to validate their process. One of the things that we believe today is that if you look at the soldering materials that are being manufactured today in the technology, they're very good materials, and most of them are no-clean materials. They're designed to repel water, which is the catalyst which causes all failures. And so if you look at what has happened, some of the components are different than other components, and some components can trap residues, they have a high thermal mass, and are more problematic than others. So just as what Graham said, other techniques such as surface insulation resistance testing could be more valid for a certain assembly type than the ROSE testing. It's not to say the ROSE testing has to go away. If it's meeting a certain criteria today, it can continue to be used based off those changes that are being done in J Standard 001.
So, Steve, you're obviously fairly heavily invested into ROSE testing with your latest system. Would you agree that you need different sizes of, the 1.56 is a fairly arbitrary size, and it needs to be varied depending on what you're actually testing?
Well, Graham, I think 1.56 is really, a number that historically has a lot of support for it, because it's been the standard for 47 years actually, since 1971. And although it isn't a true test that will identify ions, it is a test that does identify the total ionic content that's soluble in the extraction solvent. Now that does leave the possibility that you're not extracting some of the flux underneath the components and things like that. But I see it very much like driving a car and having a speed limit, basically. So if you have an Autobahn in Germany, you can drive as fast as you want. And that limit sometimes is only because you have tested the cars and you've tested the road and you know what the conditions are of that particular environment. In an electronic manufacturing environment, that ROSE test provides a speed limit. And although it may not be totally encompassing in terms of what it says, it has prevented for 47 years really bad catastrophes from happening. So the reason that the ROSE test was originally implemented was because we had a lot of catastrophic failures in the very early days of electronics industry, primarily in the space and the military areas. The most notable one being the Apollo catastrophe that happened in the late 60s. It was never positively identified as the cause, but the most likely cause that was identified in there was residue remaining on a circuit board that initiated a fire and then destroyed the capsule. We have a lot of other military examples in the early 70s where we had systems failures, Harpoon, Shrike, Paveway missiles and things like that, where we did pin it down to contamination on the board. And at that time, ROSE testing really was our best route to look at. Although the military specifications did call for SIR testing and a qualification regime of SIR and other tests that would qualify the process, and then once it was qualified, the ROSE testing could be part of that qualification or not, but the ROSE testing was used to control the process along with visual examination being your two primary ways you control your process day to day. So I think it's a little bit dangerous to eliminate that speed limit that we've had for 47 years without identifying what the objective evidence is that we want to have to replace it with. And in the new proposal, it does say that in the qualification, we have to have objective evidence. That's the same as we had with the military specifications and what have you before. But the difference being that this is a process control tool. It's really not a qualification tool. So, I think it should be used as a process qualification if you want, but really it's process control. And if you're going to have a process control tool, you need to have limits on it. Whether you use 1.56 or 1.0 or 0.05, it's important to have a speed limit for your process and for your product. So that's my position.
Yeah, sure. First of all, I would like to highlight one important point. We from automotive industry normally do not clean products. Yeah, so I would like to really stress this point. We use no clean fluxes. 90% of our products are not cleaned for the automotive electronics. So motor control units, airbags, ABS, ESP systems, steering control units are not cleaned. And they are highly reliable in the end-use environment. And we are using, or we are achieving these highly reliable products by really intensive high humidity and high temperature testing. So on a very first step, we trust that only an SIR test is the most important and most relevant test for check if all the materials you are using and all the processes you have done for realizing a product are okay, that all the materials processed in a correct way, and then they will remain in a safe state on the board. So this is for us the most important point, so SIR testing. Any kind of roast testing is just a flanking activities. So we do it, for example, just for finding best process settings for selective flux application. Yeah, then we can do a roast test, we see different readings and can find out what is the optimum setting. But we have a lot of discussion with customers when I'm talking about this approach and the mindset behind. They all agree, yeah, that's fine, but at the very end, one person will stand up and ask me this question, and when will you achieve 1.56? So this is totally wrong. Yeah, so this is a total, complete misunderstanding about reliability and safety, because the single value is meaningless. It totally depends on the end-use environment of the product. It depends on the layout, the voltage it is operating, and a lot of other factors.
Okay, thank you. So it looks like the panel is pretty much in agreement on the fact that the 1.56 figure is a bit arbitrary, and that that roast testing is essentially a process control system. Let's move on to look at SIR testing and how it can verify cleanliness. Maybe start again with Graham, if we could pass the mic back.
Well, SIR testing is not essentially a tool for determining cleanliness. It is to determine the electrochemical reliability of the intended end product. You do not conduct SIR testing on the actual end product. It does not work that way. It is a representative sample. So you have to look at characterizing your process using different techniques, and then control that process by something that is fast, that is convenient, that is accurate, that is sensitive, to pick up those residues that are on the surface that could compromise ongoing performance on the proper end product in its service environment.
I also agree with Graham that SIR testing is a good electrochemical test for evaluating the product acceptance of a specific design or product. We've done a lot of work with SIR testing, and one of the things that we like about SIR testing is that it gives us the ability to look at many process variables or considerations. We can compare different soldering materials, different solder paste. We can compare different cleaning processes. We can compare and look at the board in a specific component type. And we can use SIR testing to give us a good idea of the reliability of a specific design as it's being manufactured. So we like SIR testing, and we believe that it's one of the test methods that can give you a lot of information from which to make a process decision.
Fine. Okay, Steve, if you can give
Right.
us your view on that.
Sure. Over the years, I've worked for many military and medical companies, and we always use SIR testing for qualifying our process and qualifying our design. And it worked very well because, like Mike said, it really does show the differences between flux A, flux B, clean process A, clean process B. But it is not a true test of your product in the sense that, you know, you might not be using the exact same substrate, the exact same solder mask. You might be wanting to test areas under components where you have flux remaining. So you have to design the SIR test so that it truly does give you the information you're looking for on your design. If you have those tight spaces, you need to test in those tight spaces. And if you have an open board with 10 mil spaces, then that's fine. But if you're down to 2 mil lines and spaces, then you need to run your SIR coupon with that kind of qualification. But keep in mind, it is a qualification process. It is something that you would not do in production on a daily basis. So if you want to control, you need different tests to do your control. But in qualification, it is a very important test, but it is very important you run it in a way that's meaningful to your product.
Okay, that's a good point. Lothar, have you had much experience using SIR?
Yes, so I like SIR testing, so it's a very important tool for us. What we are doing is currently we totally are following the IPC 9202. So this is a very good starting point when people are not so familiar with SIR testing. And for me, it's a little bit more than a standard. It's somehow a little bit a mindset. Yeah. For me, this IPC 9202 says bring everything on the board as it is later on in series production, and then do this SIR test. So there is, of course, a recommendation currently that this is B52 board. It is quite good. There's a lot of design elements realized on this board so that you can check different solder pastes. It's also the possibility for checking influence of selective soldering processes. We apply also any kind of polymers, conformal coatings on such kind of board, and so on and so on. And we step further on already. So we at Bosch, we have developed, we call it B52 Starboard. So it's a lot of new miniaturized and leadless components implemented. So we do it at the very beginning as a platform release. So when our product teams come up with new ideas, with new design elements they would like to implement on a product, then we design a completely new board and do such kind of SIR test at the very beginning. And we push really the limits here. So we go with these boards into 1,000 hour SIR testing in order to clarify that there's no degradation over time of materials. And we are doing also damp heat cycling tests with this board, so driving this really close to the dewing point so that we can observe all the really critical reactions that can occur by chemical interactions of the materials. And if we are sure that this will work, so then we give the release for these materials for serious production, and later on, of course, in serious production we have a lot of additional temperature humidity bias tests on real products.
Okay. Well, it sounds like a very extensive SIR test that you're performing on new products. If we can move back to Mike Bixenman here, what other kinds of non-destructive testing can you use? We need to get the microphone.
Okay, the question was, what other type of non-destructive testing can you use? There are other test methods out there. For example, Eric Camden's in the audience. They had the C3 process, which allows you to, it's similar to a Rose test, but you can go more component specific, and you can extract using steam, and it's a sealed process to exasperate that fluid, and you can measure the conductivity which is a very quick test. Or you can also do enough extractions to do ion chromatography, which is typically done either off-site at a reliability lab, or somebody like Bosch has an instrument like that. They could use that. Certainly you could look at visual. Many people have looked at visual characterizations, and what we know and what we have learned is that if you partially clean, or if you can see residue, you have a really good indicator that there could be a problem if you're cleaning. If you're not cleaning, such as what Bosch is trying to do in a no-clean process, then maybe the visual is not as ideal. But visual has always been a good method. The problem that you have with visual is you can't necessarily see what's under the body of the component. And in some cases, if you desolder that with a heat method, you destroy the evidence. So one of the areas that we like to do in test boards is we like to shear the components off to a point where we don't destroy the evidence itself. But that is a destructive test method. So you asked what's a non-destructive test method. So So visual would certainly be one. Again, going back to the ROSE testing, and you know, as a process control tool, it can add some benefits in that area as well. What I always contend is that there's no one test method that's ideal for all conditions. I think you have to look at your situation, and it comes back to what this gentleman said here. What is your in-field use? Where is that board going to, what product's going to be in, what kind of environment's going to be in? The harsher the environment is, the more critical the test methods have to be to assure that you're going to have a reliable device.
That's a very good point. I mean, Graham, what other test methods do you think, you know, especially for harsh environments, you know, with high humidity and
well,
challenging?
there really aren't any other test methods that are convenient for use. Ion chromatography is obviously a technique that is used to identify individual species that are present on the circuit. So they will tell you exactly what is present, but it will not tell you whether or not the end product is going to be reliable. So they work hand in hand with each other. From the standpoint of FTIR, you can identify and fingerprint exactly what is there, but for the same reason, you can't use that to determine whether or not you're going to have electrochemical reliability in the end product. If I can just add one other point that relates back to the point of the 1.56 pass-fail level. Originally, the US Navy in the Department of Defense wanted to put a stake in the ground, and I was present at the meeting that took place back in 1987, 86, when Jack Brous of Alpha Metals, who invented the ionograph, and Brian Ellis, who invented the contaminometer, had an argument with Dieter Bergman over the fact that the US military had implemented this particular pass-fail level. And that has survived, as you rightly point out, for many, many years. But consider always that it means that it's acceptable to leave up to 1.56 micrograms of sodium chloride equivalent on the surface of an assembly. And with modern technology, that is absolutely not the case. So establishing your own pass-fail limit is paramount to successful survival in difficult and hostile environments, made even more important when you're dealing with safety critical conditions, which of course is exactly what Bosch are doing, plus add to that driverless technology and electric vehicles are certainly posing some interesting requirements as far as electronic circuit reliability is concerned.
Make a good point. Okay, if you could pass that to Steve Stach. Steve, maybe, you know, just to finish on that same question of other non-destructive test methodologies.
Right, there are, you know, as we talked about, the ROSE test, visual, I definitely believe is a very first-line test that you can use that will give you the indications you're looking for. Like Mike said, if you see visual residue in your cleaning, then you probably need to do more analysis, and that is probably the best non-destructive method you can use. Now, when I was at TI in the board shop, we were building weapon systems. On every panel we built an SIR coupon right on the edge of the panel. So another approach for a non-destructive test is to build SIR coupons into your board, even underneath very sensitive components where you may not completely outgas all and deactivate all those activators that you have. It's not something that is quantifiable in the sense of a certain level, but if you look at that day to day and you're at a certain level on that SIR and that increases or decreases, then that would be a very good non-destructive test also for checking. The problem with that is modern circuits are so dense, it's very difficult to find space under components to put these patterns. So, you know, putting it on the edge of the coupon or a break off or something like that that you could go analyze further does not destroy your assembly, but does allow you to go further test and quantify your cleaning process.
Okay. Great.
That might be another way to look at it.
Yeah, that's very helpful. Lothar, are there any other non-destructive test methodologies that Bosch are using?
Not really yet. So far ROSE and also ion chromatography so far okay. So for me it's a flanking activity. It's quite good, especially on ionic chromatography when you are doing failure analysis. So then you get a quite good idea if anything did wrong during a validation test, what might be the root cause. So for this case, ion chromatography is a pretty good tool. And as I already mentioned, ROSE is also one of our flanking activities. It is implemented in several of our plants all over the world. So giving some proof on a more or less irregular base that our processes are constant, so we have a very stringent quality systems. They must remain constant with our high volume production. So there is unfortunately no other very quick test currently available. So SIR testing is currently for me the best tool. Ion chromatography can be a tool just for minor changes. Yeah? So when we transfer a product production, let's say from line A to line B, yeah, and our customer is a little bit concerned, is everything okay with that? Then you can do ion chromatography or even simpler ROSE tests and can prove everything is same, all materials are the same, machine is the same, and now you have some evidence by doing ion chromatography or ROSE tests. Yeah? So there's no change.
Okay, thank you. Well, staying with you for a moment, Lothar. Process automation is demanding a lot more data coming out of cleaning equipment, etc. What sort of data are you extracting out of your systems, and what will you be looking for in the future?
Oh, this is a good question, so that I'm not able to get really good answers to. Industrial 4.0 is a very big topic in our company, and a lot of people are working on it currently. Yeah.
Okay. Fine, but it's still an open question as to what you're going to be looking for coming out of the production equipment, your cleaning equipment, in terms of data in the future. It's still an open question. You're still discussing it. You haven't come to an agreement.
Yeah,
okay,
that's right.
Okay, maybe pass it on back along the line to Steve. Steve, I mean, you've started with this process control tool, this ROSE tool in your system. What do you see in the future, the demands that are going to be made by EMS companies for cleanliness data coming off the machine?
Well, in terms of the machine itself, I think that what we've used historically has been the resistivity or conductivity of the rinse water as our indicator of whether we've got the boards cleaned and rinsed properly. That's a good test, but there is a better test actually, and that's looking at the drop in the conductance as the board is in there in that final rinse, not just the absolute value of that rinse water being 10 meg or whatever you program, but how much does it drop over time as that board sits in there? So if it starts out at 10 meg and it goes down to 5 as that board is in that final rinse, that would indicate that you have not rinsed it properly. You still have either detergent on there or you have flux on there or something like that. So what we're working on is actually monitoring the rate of drop in that DI water in the rinse, which is essentially the ROSE test. And we're doing it with water, and we've incorporated it into our cleaners, and now each cleaner can, if you choose, perform a ROSE test on each batch in a batch cleaner or each board as it passes through an inline cleaner. That is the best, in our opinion, that you can do, because you test every batch, you test every board, and it's automatic. The data is automatically transferred to your process control system, and that would give you not only daily controls, but actually batch or board by board controls. So if anything got out of whack, you'd know it immediately in terms of that. So I think the key thing for the future is to implement these kinds of process control tests into the cleaning process so that immediately we capture that data and notify anybody if we're out of our control limits.
Mike, if I could just pass on to you, I mean, what sort of data would you like to see coming, from the process to help improve process improvement in a sort of smart factory environment?
When people build circuit assemblies, they always want to validate a process to a certain condition, and they want to build that process within design limits. And so as we go back to Industry 4.0, that's exactly what they're trying to do. They're trying to look at each phase of the process and say, if there's ever an upset, we want to know when there's an upset so that we can go investigate it further. And you can do the same thing with the cleaning process. Steve illustrated one idea. Today, you can monitor, just like if you're cleaning and you have a cleaning chemistry, you want to make sure that chemistry stays within a certain limit. You don't want it to get out of control. So you can measure that and monitor it, and you can feed data back. And if something goes out of spec, you can go investigate it. It gives you an indicator, again, that something may be wrong, so that you don't build a series of boards along the way that could create a reliability condition down the road. And I would only suspect that that's going to get better and better with time.
Yeah, I think absolutely. I think that the goal of a smart factory is also to make sure that we're correcting as much as we can in real time, and not leaving it to a meeting a week later to say, well, this is how much we screwed up last week. So, Graham, let's finish with you on this.
I think my closing remark would be, and it's the most important, is that the industry has to adapt to the fact that rose testing is not, and never has been, and never can be, a cleanliness test. It's a very, very tough subject area, and it's going to certainly tax an awful lot of people as to, well, how do we go about things? I think what you've heard from the panel is there is no single easy solution to the problem.
Well, I mean, that's true, but I mean, ROSE is still a useful process control tool in that sense. But to do it properly, you're going to have to.
Well, rose testing per se is a perfect process control tool. No argument with that. But what you have is the need to give the production engineer a fast go, no-go answer. And the only way that you can really achieve that is as fast as possible, because you're dealing with a deionized solution, and a deionized solution does not like to be in that state. It goes hunting for material. The critique is that too many people test for far too long a period of time, and even worse, at higher temperatures, and it gives them skewed data, skewed results, which can compromise your production process all on its own. So fast, quick, efficient, effective is the key, and every single production line, because of this condition, is going to give you a different upper control limit for that particular process, because every material set will give you different values that you need to work to.
Well, interesting viewpoints. I want to, we're running out of time, unfortunately. It's been a really interesting debate. I want to say a quick thank you to all of our panel, Lothar Henneken from Bosch, Steve Stach from Austin American, Mike Bixenman from KYZEN, and Graham Naisbitt from Gen 3. And I want to thank our audience for watching, and we'll have our next debate this afternoon at, I think it's 3:15. So join us then. Thank you.